Yeah, that's a submission deadline for everybody who's kind of like submitting. So like yes, here.
All right. Well, let's go ahead and get started. We're very happy today to have Peizhi Du from Rutgers University. Peizhi got his PhD at Maryland at our Costa Agache, and he's currently a postdoc at Rutgers. So he's going to tell us about some cool dark radiation isocurvature from phase transition. Take it away.
Great, thanks. Thanks for the invitation and thanks for the nice introduction and thanks for all of you coming here. And today I will talk about our recent exciting work on dark radiation isocurvature from cosmological phase transitions. And this is in collaboration with people at Rutgers, faculty Matt Buckley, postdoc Nico, and the student Rich. Some group of people in the audience have heard a shorter version of this before, and hopefully you can get more from this longer version of this talk. Okay, so you might notice that the background of these slides, that's the distribution of the bubbles. And actually that is from one of our simulation of the phase transition we consider in our talk. And hopefully at the end of the talk, you'll understand how to generate this kind of images and how will that impact in our CMB. So that's our signals.
That's one giant bubble in the middle.
Yeah, that's of course we chose it sort of artificially we put it at the center, but there will be big bubbles.
Okay.
But not necessarily at the center. We will choose our frame to do that. Okay, so let's move on. Okay, now okay. So the main topic today is about cosmological phase transitions. So first, why do we care about cosmological phase transitions? The first reason is they exist in cosmology. Here I showed you a diagram of the typical thermal history of our universe all the way from Big Bang to today. Throughout this time evolution, there are different temperature scales. There has different kind of phase transitions. For example, in standard model, we have a QCD phase transitions around 100 MeV scale, electric phase transition around 100 GeV scales. Of course, of these two, in the standard model, these two phase transitions are not first order. But if we consider more like a BSM physics, we can have a BSM phase transitions basically can occur at any time in the earlier universe, and they could be first order. And why first order phase transitions are interesting? Because they are linked to some rich new physics. For example, we can make our electric phase transition first order by adding new physics, and we can do baryogenesis. Through the electric baryogenesis, we can explain the baryon anti-baryon symmetry of our universe. Or we can consider some models in the dark center has a SUN confining group, and the hadrons of that could be the dark matter. And could also explain original dark matter. Or we can link that to electric hierarchy problem, because one of the solutions to electric hierarchy problem are called composite Higgs models, where they have predict some kind of confinement in early universe. And that kind of phase transition is also typically first order. So it is linked to rich new physics. Second, observational-wise, is very exciting because a lot of experiments have been built or will be built probing the signals from cosmological phase transitions. The first type of signals very famous and people have heard about are gravitational waves. Here I showed you like some instruments to measure gravitational waves, like using pulsar timing array like nanograph, or ground space-based interferometer to measure gravitational waves like LIGO or LISA. And one benchmark of the gravitational waves they can measure is from cosmological phase transitions. And another type of probe for cosmological phase transition is through CMB, which probably is less heard about. And actually that will be our main topic of today. And in particular, just a heads up, the signal we're considering in the talk will be something like this. We have some kind of distribution of this like bubble-like, big bubble things imprinted on the CMB sky map. And I will show you what kind of models can generate that and what kind of signals or constraints we can get from using CMB data. So that is the target of today's talk. Okay, so here I go through the brief outline of the talk. First, I will discuss what are the typical signals considered in this kind of phase transitions. And we introduce the model we consider, the slow first order phase transitions during inflation and how the bubbles generated and evolved in this kind of phase transitions. And we're talking about the isocurvature signals of dark radiation from the phase transitions. And then we move on to the signals on CMB. In particular, we care about 2-point functions, 2-point it's an angular power spectrum, or 3-point functions, non-Gaussianities from these type of signals. Then we'll comment about future directions, and I will conclude. Okay, so let's get started with the first part is what kind of signals we can get from cosmological phase transitions. And one signals I mentioned before are gravitational waves. And now it is a very hot topic. And here I showed you on the right a cartoon picture how to generate gravitational waves from these first order cosmological phase transitions. Here you see that some kind of when the phase transition starts, the first order, they nucleate the bubbles, and inside the bubble is a true vacuum, and outside the false vacuum. And those bubbles will expand, and they will collide, and then take over the whole universe into complete phase transition. While the bubbles they collide, a lot of energy release from this kind of collision, so that will source gravitational waves, and that is one source of the gravitational waves from bubble collisions. During this process, depending on the model, you could also have a plasma around the bubbles, and they can source they'll have sound waves in the plasma or turbulences in the plasma. Those are also could source gravitational waves. So these are combining of all of these are one of the benchmarks that is like these are like interferometers we're looking for.
Quick question. These are sound waves in the MEV universe, not baryon photon sound waves, like much early plasma sound waves. Is that right?
So for electric phase transition, it will be the standard model plasma around that scale, of course. Yeah. And yeah, so it's during this process, but they also can perturb the plasma, and that also source gravitational waves. Okay, so actually the main focus of today is on the signals on CMB and what type of signals we can get from cosmological phase transitions. So first we need to make assumption that if after phase transition, most of the energy during phase transition convert into dark radiation. And what is dark radiation? Is some kind of light degree of freedom in the dark sector, which behave like a radiation during CMB time. And if you have that kind of assumption or model, there is a constraint is that what is the energy density of that dark sector or dark energy at the time of formation of CMB. And typically we use a parameter called delta N effective, which is defined like this: the density of the dark radiation over the neutrino density times 3.044, and 3.044 is a standard prediction from standard model of the neutrino species. So because I have 3 neutrino species, it's close to that. So basically you think about what is the effective number of species of neutrino, which is in the dark radiation. And currently, CMB can put a constraint on that. Planck collaboration in 2018 put a constraint of delta N effective is 0.3, which is like 10% of what we could have in the neutrino sector, which is already pretty strong. However, there's a big assumption built into it that they assume adiabatic initial conditions for the neutrino sector, or for the dark radiation sector. Now, what is the adiabatic initial conditions? Here I showed you on the right a cartoon picture. What is adiabatic initial condition? It shows that all the perturbations in the radiation, like photons, neutrino, now it's the dark radiation, initially, they're all the same. Delta is a dimensionless density perturbation, is delta rho over rho. So all of them are the same initially. So that's called adiabatic initial conditions. And actually, that's a natural consequence of the inflational models, because the source of these primordial perturbations are from inflaton fluctuations, and they're coming from the same source. So that's why they are the same or correlated, and that is why it's called adiabatic. Okay, now if we consider more flexibilities, some new dynamics, you can source isocurvature. In particular, I want to argue that the phase transitions we considered in this talk will generate isocurvatures in the dark radiation, and you will get much stronger bonds. So first, what is isocurvature? In short, any initial condition that is not adiabatic is called isocurvature. And in this talk, I will mostly focus on isocurvature, mostly in dark radiation. So we call it dark radiation isocurvature. And the basis we define this isocurvature is cartoon pictures look like this. that's the density of all the radiation perturbations, photon, neutrinos, and dark radiation sum up to 0. Notice this is density, not the density delta rho overload. It's just density. Once we have this set at the initial time, because this is the source of the curvature, so the source of the curvature is 0, so there's no source for curvature, but it will source isocurvature. And that is why we define this as isocurvature basis. And in our talk, in our paper, we showed that if we consider dark radiation from phase transitions, we can get a much stronger bound on delta and effective. We'll study this isocurvature on CMB, where the T star is the temperature when the phase transition completes, and the TRH is the reheating temperature of the universe. So you can see if the temperature of the phase transition is close to the temperature of the reheating temperature, we'll get a much stronger bond compared to the naive adiabatic ones. And I will show how to get that at the end of this talk. Okay, let's move on.
Wait, what's T star here?
The temperature of phase transition.
And the reheating, you mean like the reheating from inflation? These are.
Yes.
So you just the standard picture, you reheat up here, and then somewhere later on, there's a phase transition, and it's that ratio.
Yes. Yeah. Okay, so now before I move on to the detailed models, I want to have some general argument about isocurvatures, because maybe not all of you are very familiar with isocurvature. So first, I want to argue that isocurvature is a generic feature for any dynamics to generate some perturbations not from inflation, not from inflaton. In particular, here we're talking about phase transitions. Phase transition is a different dynamics than the inflaton fluctuations. So the dark radiation, which is generated from the from phase transitions, will generally have isocurvature, because we said anything that is not adiabatic is isocurvature. And then the next thing is, what are the features of this isocurvature? And the features we'll care about really for observables are power spectrums. Here I showed you the power spectrum of the isocurvature, and as the P is a 2-point function, K is the comoving the wave number. So the typical scale when we consider phase transitions is the comoving horizon scale at the time of phase transition completes. T star is the temperature when phase transition completes, and this is called T star. There's a universal behavior for K's smaller than K star, which behaves like KQ. Why is KQ? That is because you have some dynamics with some horizon of this size, but on the super horizon scales, there's no correlation. And if there's no correlation in position space, in the fluid space, it's a constant. But now if we define our power spectrum as a dimensionless power spectrum, normalization, this KQ will be just from the measure of the D3K. So it's a behavior like a KQ in the super horizon regions. And also that is also a behavior for the white noise, if you are familiar with that kind of language. So then I would argue this is a universal behavior for any dynamics that is super horizon to any to a certain scales. And for scales smaller than K star, which is sub-horizon for the phase transition dynamics, that is model dependent. Typically need some simulations to get a more reliable result for that. So I use a dashed lines here. But this like super horizon scales is more robust. Now we want to, now you might wonder, since I argue that this is a generic feature for any new dynamics, why we haven't heard about that much on the CMB constraints for these things. That is because there's a big scale separation. Let's look at the scale that CMB can probe, which is the temperature of the CMB is roughly around EV scales. Now, if you consider some phase transitions happening at a high temperature, let's say you're at TV or some even higher temperatures, there's a big scale separation between the scale of this K star and the scale of the CMB. And these two separations KQ. So if you have some amount of scale separation, the power spectrum from isocurvature will be suppressed by KQ by a lot. So that means the KQ, the isocurvature behavior, the signals at the CMB scales will be much suppressed, whereas the usual adiabatic ones will take over. So that's why people will not, you might not hear much about the isocurvature signals at CMB from phase transitions. Okay, now then you might ask next questions. How can we get signals or constraints from the from CMB on isocurvature surfaces. The one natural reaction or thought is, why not bring these two scales closer? Because I said there's a big, there's no constraint because the scales are well separated. But what if we bring them closer? Indeed, people do consider these low scale phase transitions, as a few papers showed here. In particular, models are interesting because there are Hubble tensions, and one of the solutions to the Hubble tension is called early dark energies or new early dark energies, where they invoke some late time phase transitions around EV scale. They said they can address the Hubble tension, and that's why they bring up a lot of attention on these low scale phase transitions. People do consider that. In this talk, we will explore another scenario, which also we found very interesting, is the slow first order phase transitions during inflation. And that is our favorite. Okay, now on to now you might ask, why do we need to consider phase transition during inflation? What is slow? Here I want to introduce all the ingredients one by one. First, I want to argue, why do we want to consider inflation? Here I showed you a diagram of the co-moving length as a function of scale factor, and the time goes this way and goes to the right. And here on the right, this is the radiation domination era, which is after inflation, and this is CMB time. And the black line is the co-moving horizon. So we see that there's another place we can get the co-moving horizon length as large as the CMB size in the early universe. That is during inflation. Because you see you can draw this dashed line, there's another time we cross that is during inflation. Because during inflation, if you trace back in time, the co-moving horizon grows. Okay, so that means if we have some dynamics happening around here, and the co-moving horizon scale is as big as CMB, so once of course, they will be exiting horizon during inflation, and then they will re-entering horizon during CMB time, and you will get a signal as big as that can be observable at CMB. Okay, that's why the first reason why we do consider inflation. Second, so what are if we have some phase transitions during inflation, so what's the size of the bubbles? Here I want to argue that the size of the bubbles is as large as the co-moving size of the horizon at the time of formation. Why that's the case? Here I showed you here. Here I showed you a cartoon diagram. If we consider phase transition in a chi field, which is another scalar field, it's not infinite time, it's another scalar field, and which has a small energy density. That means it does not affect the inflationary dynamics. So it's a spectator has small energy densities in a scalar field. It will start phase transition at some time, we call it AI. At the initial time, we start phase transition. And the co-moving horizon at that scale is Ri. So first I want to argue that the biggest bubble, the first bubble, the nucleate, will be of that size. Why that's the case? Because when bubble nucleate, they will grow. But once they grow to the co-moving horizon size, they'll be frozen because it becomes super horizon. You're frozen to the size, and that's why it grows that big. But of course, the phase transition will continuously producing bubbles, but at later time, co-moving horizon is smaller because co-moving horizon shrinks exponentially during inflation. So the later time, you get the bubbles, but they're smaller. And now it comes to another ingredient, it's slow. What do we mean by slow? Slow meaning the phase transition rate per volume is much smaller than the Hubble of inflation to the fourth power. So that is the criteria saying that the phase transition does not complete during inflation. It starts in nuclear bubbles, but it does not complete. But why we want this? Because once they complete, if they dump everything into dark radiation, and now it's during inflation, so all the energy density inflates away. So you don't see any signals at the end. But if we consider this slow first order phase transition, then it will be so the bubbles will be there, but they never collide because they never complete phase transitions. So you just an imprint of these bubbles in the chi field and remains after inflation. Okay, so that's a feature we want to consider slow. So here I showed you how the time evolution, if it evolves at a later time, horizon even smaller, you get more of these small bubbles. But what happens after inflation? So after inflation, things change. One thing changes is the Hubble parameter drops. Because now we're in the radiation domination era. Hubble parameter drops, whereas during inflation, Hubble is a constant. Hubble inflation drops. At some point, this equation was satisfied, where the rate of phase transition per Hubble per volume can be equal to Hubble parameter at some time we call it T star. At that time, fission completes, because now we can nucleate 1 bubbles per Hubble volume, and at that time, so fission will be complete by bubble collisions at that time. So at that time, fission completes, that defines T star. At that time, the energy density in the bubbles will be converted into dark radiation, and now because those big bubbles are super horizon to the scale of the phase transition, so those big bubbles will still be there because they have never entered horizon yet. So that means the dark radiation still inherits these perturbations of superhorizon perturbations from the chi field, and that is a isocurvature in the dark radiation.
Are these relativistic modes of chi, or are you dumping it into other degrees of
Other
freedom?
degree freedom. So we couple this to some light degree freedom. Let's say some light fermions, dark fermions, which is not standard model. So it's so those are dark radiation. Yeah, so we need additional degree freedom. Okay, good. So now you might ask, what kind of models you can generate this, or what kind of phase transitions we consider? And you might think maybe some exotic phase transitions. Actually, it's not. I want to argue that it's a generic feature for non-thermal phase transitions, complete after inflation. What do we mean by non-thermal? Meaning that the order parameter is not temperature. So we don't need temperature to trigger a phase transition because we want the phase transition to start during inflation. There's no meaningful temperature parameter during inflation. So we want some non-thermal phase transition. And in particular, we want to the non-thermal we mean is the phase transition rate gamma PT is independent of temperature, is a constant in time. And if that's the case, and the phase transition completes after inflation, we will argue that the slow rate condition is naturally satisfied. Why that's the case? Here I showed you the diagram and also again scale factor. Y-axis is the rate per Hubble to the force, and that is the parameter controls when the phase transition completes. If it's 1, that is when it completes. So we consider this is 1 at some time after inflation. Let's call it A star. Now, if we trace back in time, because Hubble, if we trace back in time, Hubble grows at temperature squared, so Hubble to the force grows at temperature 8th power, and this rate drops as 8th power of the 8th scale factor. So it drops very quickly at the time of inflation, and during inflation, because Hubble is constant, becomes flat. And we will see that this rate during inflation is much smaller than 1 because it will be 8th power suppression if there's some natural suppression between these two parameters. So the slow condition during inflation is sort of naturally satisfied. Okay, then what are the models? So actually, I want to try to say that you don't need a very fancy or exotic models. Maybe the simple model, or even the simplest model we first considered when we study phase transitions is sufficient to generate this kind of signals. And here I showed that's a Lagrangian, basically some tree-level Lagrangian for the scalar field. And we have the chi-square, chi-cube, chi-4, and we arrange that the mu, we want to enforce a mu parameter is small. That means if mu is small or 0, so this has a Z2 symmetry. So mu can be technically naturally to be small, the technically natural. And we have the negative mass square, so we get the double well potential like this. But because of mu, so one of the potentials is lifted up, and then we can consider, and the vacuum energy difference between these two vacuums is proportional to mu. You can calculate that. And the phase transition will start from the first vacuum tunnel to the true vacuum. And we can calculate what is the phase transition rate using the usual bounce actions. So the phase transition rate over Hubble to the force is proportional to e to the minus S4. S4 is a bounce action, O4 symmetric bounce action. And we can calculate it in this simple potential. It just goes per metric like this. This goes as 1 over mu. So small mu is technically natural, which can make this potential, the delta V small, and also give a small phase transition rate. So it's all like connected. And so we can get and mu is technically natural, so we can make it naturally small. And the rate will also be small because of this exponential factor. Okay, so that's good. But now there's another feature I didn't introduce, and because I mentioned before, where there's a time when the phase transition starts. But in this model, there's no time when the phase transition starts. It seems like it will be there as long as the time starts. So how to model the start of the phase transition? Here I want to see what the model way. So ways to consider is we're adding some kind of switch function or trigger function to promote mu as a function of phi. So as I said, we want to consider some non-thermal phase transitions. There's no, and also during inflation, there's no temperature as an order parameter. But there's another order parameter or clock during inflation is the infinite time field. Because infinite field we consider slow roll inflation. So there will be the field value of infinite time scans. So that acts as a order parameter or clock. So now we can couple our high field to infinite time, and we promote that mu parameter to a function of phi. And the function of phi we consider is some kind of tangent H function. So it mimics some kind of step function. So this is one of our realization of that kind of thing. Of course, this is, I want to say this is the only one. You can plug your favorite models, have some kind of switch function like behavior, and all the phenomenology signals we are considering today will also apply to that kind of signal. So this is just one of our models for that. Okay, once we have this, what will,
This is a very weird coupling. Like, is there any sort of natural inflationary scenario where you get something like this?
Yeah, the first one we look at is very exotic, but if we look at literature, people do consider some kind of alpha attractor inflation models. So they, I think, inspired by some string theories. Maybe some expert here can comment on that. And one type of that you can get the tangent H functions of that. Not exactly this form, but tangent H function can appear.
It exists there, some
Yeah,
model
some
there.
models of inflation can exist there. And also, yeah, so I said this is one model. You can plug your favorite models, which have this kind of switch function like things. This features will appear there. Okay, so once we have this, functions, what's the time evolution of this model of phase transition is at sufficient early time when phi is smaller than phi I. The phi is some kind of field value is a constant, field value of the infinite time, and delta phi is some kind of width of this transition is also a constant we put in by hand. And at some early time when phi is sufficiently smaller than phi I, this parameter is negative. So the chi plus vacuum is a true vacuum. So it will be stay there. But once when phi scans across phi I, and then this field value has been lifted up because phi will become positive, and now the phase transition starts. So the time when phi equal to phi I is the time when phase transition starts, and that is why we define this AI as a scale factor when the phase transition starts. So that's adding a new feature is the start of AI. Okay, so now let's look at the dynamics of these phase transitions. So we consider the phase transition starts during inflation and bubbles start to nucleate. And what is the size of the bubble? Here I want to argue that the size of the bubble corresponds to the comoving horizon size at the time of formation. And there are two ways to understand it. The first way is to understand it in the comoving coordinate. In the comoving coordinate, and then when the bubble generates small, and then it grows to the comoving horizon size. And once we reach the comoving horizon size, it becomes super horizon, it'll be frozen there. And there's another picture to understand is in the physical coordinates, where the physical horizon is always constant. And the bubbles are nucleating at the sub-horizon, but bubbles and the horizon grow together because inflates. But early bubbles, because they have a longer time to grow, so it becomes bigger together as a horizon. So that's why the bubble size corresponds to the comoving horizon size, and the early bubbles is the biggest. Early bubbles are bigger bubbles. And now this is from one of our simulations of these bubbles with the three-dimensional coordinate, this x-axis, this y-axis at time 0. That is the time when we start the phase transition. And Ri is a moving horizon size at the t equal to 0. Okay, as time evolves, the more bubbles generate because they generate at a later time, the moving horizon shrinks, so we get smaller bubbles. Now, because we consider incomplete or like a slow force over phase transition, these bubbles do not collide because they are sort of far away from each other. And here I see, because here you might see like bubbles might be overlapping in this kind of image because it's a 2D projection of 3D. It's actually they're not overlapping in the 3D. We use the color to indicate the the z coordinates. So they are not overlapping. Even at a much later time, we get more and more bubbles. They are not overlapping with each other. So phase does not complete. And also you can estimate what is the fraction of the space occupied by bubbles. So what is the fraction of the true vacuum in that space, which is actually the same proportion to the same parameter, gamma over Hubble to the 4th, which is much smaller than 1. So you can imagine that when the friction starts, bubbles nucleate, but the rate is very rare. So you nucleate a bubble here and sometimes here. But after end of inflation, the bubbles never find each other. They're just frozen to their size and spaces keep inflating. And the true vacuum, the fraction of the true vacuum occupied by bubbles is a small fraction. So most of the space is still forced vacuum. The fission does not complete. Okay, so that's the picture of the dynamics of the formation of the bubbles during inflation in this kind of fission models. Okay, now we move on to another important ingredient is in order to link to observables, what we care is about density perturbations in this type of models. And the density perturbations is the delta rho over rho. And how to get delta rho at first place? So delta rho is the energy density in the Kite field is because inside the bubbles, that's a true vacuum, and we set the CC of true vacuum to 0. And outside the bubbles in the forced vacuum is some delta V. So the density perturbation is generated because once you have a bubble, you have a 0 energy density where the rest is delta V. So that generates density perturbations. And I want to also emphasize the biggest bubble is corresponding to the Ri, which is the time of the co-moving horizon at the formation at the start of phase transition. Is the biggest bubble. Now, what we care is, as I mentioned before, it's a 2-point functions for the power spectrums of these density perturbations. Here I showed you we calculated the power spectrum from the simulation we got before, and with x-axis is k vector, but now we normalize to Ri in the size of biggest bubble. Now it's make it dimensionless, and the y-axis is the power spectrum over gamma pt, where gamma pt is a dimensionless parameter we define as gamma over Hubble to the 4th, and we demand it to be small for this slow force over phase transitions. And power spectrum is a 2-point function of this dimensionless density perturbation, delta rho over rho, and 2-point function of it. And here I showed you different colors correspond to different gamma pt we consider here. Now, by staring at it, there are some two different regions we can understand and two different kind of physics. Let's first focus on the superhorizon scales for small k. For small k, all of them behave like a k cube, and that is the universal behavior I studied before. Because these are superhorizon modes, there's no correlation in position space. The Fourier space goes like a k cube, and all of them follow this. And the transition is around k gamma I, k Ri is close to 1, because that's the size of biggest bubble. And if your scale is larger than the biggest bubble, there's no correlation. And that is naturally into that scale. It's also interesting to look at the subhorizon part, which is this large k part. It looks almost flat. Why that's the case? Because there's kind of scale symmetry or like a conformal behavior in this kind of models. That is because let's look at in the physical coordinates. At the time, every time you can nucleate a bubble, the rate is the same because gamma over Hubble to the 4th is the same. and everything we consider is a constant. So it have the same property to nucleate bubble. And the next thing we consider is what are the force vacuum that we can nucleate bubble. Since I argue that the true vacuum is only occupied by a little amount of energy density, little amount of fraction. So every time you can nucleate bubble, the space you can nucleate a bubble is almost the same because all the space is mostly occupied by force vacuum. So that means at any time you can nucleate bubble, the rate is almost the same. So that's why you get this kind of scale invariant behavior at a small scale. But that's typical to this kind of models. Now you can see there's a feature to validate that because if you increase gamma, little gamma become larger and larger, they deviate from this behavior, and if you increase little more, you will see there's a deviation from this flat. That is because you are violating this sort of scale invariant behavior. Okay, so that's the features of the power spectrum in the Chi field. Now we'll move on to the next stage is what happens after inflation and how to generate isocurvatures in the dark radiation. Here I showed you the cartoon picture. So here I showed you this picture again. At early time during inflation starts and the bubbles are nucleated. Early bubbles are bigger bubbles, but all the way during inflation, they generate all the bubbles across different scales, and some of them are small, some of them are big. Okay, what happens after inflation? So after inflation, Hubble's parameter drops as a t square because in the radiation domination, and the phase transition will complete at some point. And now we are reaching the scale of A star when the phase transition completes, and at that time, the energy density in the Chi field dump into dark radiation by coupling to these dark radiation particles. Energy density dump into that, and that phase transition will complete by the bubble collision, and those bubbles are small bubbles because those are bubbles of the size of cosmic horizon of this size. And that's the scale of the phase transition complete. What happens for these big bubbles? So this big bubble will still be there because there's no dynamics can erase that yet. So that's big bubbles will still imprint into the perturbations in the dark radiation. So that's why I said here, when the phase transition completes, energy density in the Chi field dump into dark radiation. So the initial condition for this dark radiation become the perturbations of the Chi field. And so those are sort of the same. And that's generated isocurvature. So what is the definition of isocurvature? So there's a gauge invariant way to define isocurvature is defined by this sort of relative entropy perturbations. Contrast is the entropy of the one species relative to the other one. In this case, we can write it into a delta of dark radiation minus photon because photon is our reference species. And in this case, it's not equal to 0 because the density perturbation for the dark radiation from Chi field, which is not sourced by inflation, like the inflaton. And so that's why these two are not the same. So there's a net isocurvature in dark radiation. In order to generate any observables, let's say from CMB, what we care is a power spectrum. What is the primordial power spectrum isocurvature, which is a 2-point function of this S parameter, and 2-point function of that will be present here is a 2-point function of the dark radiation, which become a 2-point function of the Chi field, and we calculate this from our simulation before. So the power spectrum of the Chi fields directly linked to the isocurvature power spectrum in this dark radiation. So to summarize, the dark radiation from this type of phase transitions inherits these large scale perturbations from the big bubbles generated during inflation. And we will see how that kind of perturbations imprint on the CMB and how to get constraint from that. Okay, now we'll move on to the signals from at the CMB. So because now that's the main focus of the signals of today's talk. So what are typical signals we consider from CMB? The typical signals we consider are the temperature fluctuations, because we measure that CMB is mostly like a black body, homogeneous with some temperatures, but with tiny fluctuations. And the tiny fluctuations is measured denoted by delta, is delta T over T. And then to get the summary statistics, we only consider 2-point functions. And the 2-point functions, we usually call that the CL, is the angular power spectrum. And for the usual case, the angular power spectrum is the integral of the delta, capital delta photon is the transfer function times the primordial power spectrum. And integrated of that, we get a CLTT. In the standard non-CDM case, we consider initial conditions as adiabatic. So that's why we only consider adiabatic mode and label it as AD here. And the adiabatic primordial power spectrum is denoted by this with some kind of amplitude AS with some kind of this ms minus 1 power law, and ms is close to 1 because it's nearly scale invariant. So that's a non-CDM non-CDM model. So in this talk, because we have our isocurvature, so we need to add a new ingredient to calculate the CLTT, which is adding a new piece of the isocurvature piece. We need an isocurvature transfer function and isocurvature power spectrum. And isocurvature transfer function is determined by which type of isocurvature you consider. In this case, we consider dark radiation one, and that will fix what is the transfer function here. And another part is what is our isocurvature power spectrum. And in this case, we consider this kind of phenomenological model with a broken power law. At small k, we consider as a k cube behavior, and that is, as I said, is a super horizon behavior for the generic phase transitions. And for the sub horizon, we put a constant. So that is a consequence of the model we consider. And we make the amplitude as some this F isoparameter, which is a relative amplitude difference between the isocurvature one and the adiabatic one. And AS is the same AS as the adiabatic. And then there's another scale, which is Ki, is a transition of this broken power law. And here the cartoon picture is because we have these big bubbles and the imprinting in dark radiation, and once they re-enter the horizon, it will also affect the CMB observables. It'll be roughly like these big bubble distributions on the sky map of CMB. And here we can map of these phenomenological parameters to our model parameters we considered before. So this amplitude, Fiso squared times AS, is proportional to the gamma PT, which is the gamma, the phase transition rate over Hubble to the force. And we can also rewrite that into the temperature of phase transition over reheating temperature to the 8th power in this relation. And the Ki is the inverse size of the biggest bubble as a scale of the co-moving horizon at the start of phase transition. So that gives you the mapping of this phenomenological prime transition to the model we considered in discussed before. Okay, now we are looking at what kind of what more like quantitatively what is the signals of the CLs compared to non-CDM. Here I showed you our simulation from the class using class code, the Boltzmann solver. We modified it to implement our isocurvature power spectrum, and here is the result. So first look at the figure on the left. Here is a typical figure we see as a function of L, is the L mode of the CMB, and Y is the CLTT minus CLTT from the lambda CDM prediction. And the different curves correspond to different assumptions. Now first look at the green curve. So the green curve is the model with adiabatic initial conditions and some amount of dark radiation. And dark radiation we consider in this case is 0.1 of delta effective. And so this is the green one is just a purely adiabatic contribution of a dark radiation. That's the green one. Now if we're adding actual isocurvature to it, and isocurvature follow this power spectrum, so we need to specify what is Fiso and what is Ki. And Fiso in this case we feel to be 10, and the Ki is for these two curves, the two different Ki's. And basically K pivot is some typical reference scales like Planck collaboration considered, which is 0.05 inverse meg per second, just some constant. Okay, for these two different curves, first we look at for the large L behavior. So they are the same. So the blue and the orange, they approach the same value for large L. And large L corresponds to large K because they are also probing the same plateau of this isocurvature power spectrum. So that's why they approach the same. But they deviate from that at the different scales because that is when this Ki, the transition happens. For large Ki, the transition starts earlier and they deviate from this behavior. And eventually they approach the adiabatic one. because this becomes smaller and smaller and goes back to adiabatic ones. And where the blue ones, the Ki's transitions later, so it become deviate from that at the smaller L's, and eventually they will go back to the adiabatic ones. Okay, question.
So I get that the phase transition can happen sort of like, it just has to happen before some time during inflation, and you get bubbles at effectively all scales, right? But if it happens like really, really early after like 1 equal or something,
Mhm.
like wouldn't there also be some probability that our universe just happens to be inside a really, really big bubble?
Yes,
And like, our horizon never reaches the edge of that bubble.
that's a possibility.
And so then we just see nothing, right?
Yes,
Yeah.
that will say nothing. So that's why there's a parameter we control is the Ki or the Ri. Because that's why we want to add these parameters. So if we don't add this, so that means inflation or the bubble depletion goes on forever. We could be in one of the big bubble, there's no signals. And also more than that, it's really hard to calculate the power spectrum because a lot of statistical fluctuations, because you have a horizon size bubbles. So you are limited by statistics. So that's why I want to invoke this kind of the sort of cutoff of the things. Because if your biggest bubble is smaller than the co-moving horizon now, we can have enough statistics to calculate robustly. So that's why we want to add that parameter. But indeed, if you allow the filtering to start sufficiently early, we could be in an interesting regime that we are in one of the bubbles, no signals, or half of the universe is in one bubble, half of the other one. So you might see that kind of signals. Okay, here on the right, I just want to maybe more clearly see just a purely isocurvature behavior when taking the reference to the adiabatic power spectrum, adiabatic angular CLs with dark radiation and with a different isocurvature ones. We're taking the difference and then normalize to that. So 0 meaning they are the same as adiabatic ones. In this case, it has the dark radiation, whereas non-Gaussian does not have dark radiation. So here it's more clearly you see this behavior of this isocurvature power spectrum. And high L corresponding to high K, all of them are probably in the same plateau because we fix the FISO to be the same. No matter what the Ki is, they eventually will probably do this plateau. But different Ki, they transition from that to 0 at different scales, and the higher Ki transition from earlier, and the smaller Ki transition from later. Eventually, they probe on to 0 and go back to adiabatic case. And this 4 of is proportional to KQ. And that is because the consequence of this power spectrum is considered. Okay, once we see that, we can now push, using run the MCMC scans to apply into the real data from the CMB, or now we consider the 18 and plus BAO data set, and we run through the MCMC scans, and we get a posteriors of that. Since now we have 3 parameters, we have FISO, we have Ki, we have delta effective. In order to project them to 2D, so we fix one of them and we plot the rest 2. So in this first plot on the left, we fix the FISO, we fix the amplitude, and run the constraint as a function of delta effective and the Ki. So we will see that for sufficiently large amplitude, and then it will be allow for very small delta effective, and especially if you're looking at it for these scales for small Ki, that means you are probing more like a flat, almost flat potential of flat power spectrum during CMB, you get a much stronger constraint. Whereas if you go Ki is large, is away from CMB scale, you get a weaker constraint, which makes sense because if all the power spectrum where have support is outside the CMB window, you don't get much constraint from CMB. That's why the bound is weaker and for large Ki. Maybe it's more interesting to look at the constraint from the right plots. If we fix the scale of the transition and what is the constraint on delta effective, here I see we'll fix the Ki to be different values, and we plot at the plots of delta effective, and y-axis this axis is the delta effective times FISO, because the physical observable actually is proportional to this combination squares. So that's why we proportional or we plot this combination for small Ki, and we see this kind of behavior. When a delta effective is large, we are reaching more like this constraint is more like 0.3, and that is goes back to the usual adiabatic ones, and most of that is coming from because you also perturb the background. If you have large enough density in that radiation, you also change the evolution of the Hubble, and that will also put a constraint on how much of the dark radiation you could have. So you are approaching like 0.3 for the large end. Interestingly, if you have going back to the small delta effective, you are limited by constraint from this compilation. Now I summarize it in this chart here. For Ki is much smaller than the K pivot, it's 0.05 inverse meg per second. The constraining is mostly constraining on this compilation. And if you read out from here, it's in log, it's around order 1. So this compilation should be constrained to be less than order 1. If you rewrite that into the model parameters of these phase transitions, of the FISO is equal to this combination, and AS is 10⁻⁹, we get back to this this kind of parametrics. Delta effect is less than 10⁻⁵ over T star over T reheating to the -4. So notice that this equation is only valid if T star is close to T reheating. And otherwise, you might say if T star is orders of magnitude smaller, this might be bigger than 1. Of course, that doesn't make sense because you always go back to this region. You should be constrained by the usual adiabatic constraint. This is only valid in this region for small delta effective. Okay, so that is the result we get from this MCMC scales. Okay, any questions so far? We move on to the 3-point functions, which we found also very interesting. So most of the CMB studies and maybe you might see, and also what we discussed before, are focused on 2-point functions, which is a natural consequence of the usually inflation models, because most of the inflation fluctuations are random Gaussian fields, which is only you get a 2-point function, non-vanishing 2-point functions, and get a vanishing 3-point functions. So there is a test of how good that kind of Gaussian random field assumption is to measure what is a 3-point function. So here I showed you the cartoon picture. The 3-point functions, you can measure the 3 temperature fluctuations on the CMB sky, and we do the 3-point correlation functions of that. As I said before, in the standard inflation models predict the 3-point function either to be vanishingly small, not exact 0, but to be very small. So if you measure any non-Gaussianities from the 3-point functions, then that's some hint to the new physics. Okay, so how will people usually do that in the standard analysis? Because there are a lot of degree of freedoms in these 3-point functions, you need to constrain them to some sort of templates, then to derive a constraint on these parameters. Usually we call it FNL, it's like one-dimensionless parameters to parameterize how much of non-Gaussianity it is. But in order to get that, we need some templates. And the typical templates people consider, then here I showed 2 of them. One is called equilateral, and which they assume these 3 K vectors are close to be the same. It's like a equilateral triangle. Or in the squeeze limits, where 2 of them are much larger than the other one, it becomes like squeeze the triangle. So once people doing these 2, they can get a meaningful constraint on FNL, these 1 parameters. You might see that if you apply the same analysis to our models, it's not good to pick up none of these templates is good to pick up our signals. And we argue that we need a dedicated searches to look for these kind of signals, because we have some bubble distributed on CMB sky, and none of these 3-point functions, 3-point templates will fit efficiently for this type of models. But what we can do, what we can do now is do some estimates. We pick one of the templates which is closer to our, we calculate the 3-point function for our models, and we pick one that is closer to our models, not exactly the same. And the one we pick is, Planck collaboration has studied neutrino isocurvature non-Gaussianities with equilateral configuration, which is unique configuration. And we use that to project or estimate what is the constraint of our models, which is estimations result goes like this, with a different combination of the parameters. Then now it goes like Gaussian effective cube, because we have 3-point functions, and FISO squared is less than 10 to the minus 4. Notice that here I summarize what is the constraint from the true point function we got before, is this combination to be smaller than order 1. If we plug in back in here, we could get a much stronger constraint on delta effective if we do a proper study of these non-Gaussianities of the 3-point functions. Okay, so that is why we found it very interesting, and we also try to have like follow-up works on how to find a more like a more proper analysis of these models in the semi-sky map on non-Gaussianities. And that's what related to the future directions I want to comment on. Okay, by the way, any questions before we move on to future directions?
Yes,
Yeah.
so there could be other things that also source the same isocurvatures, and can you distinguish between different, like how do you know that it comes from a phase transition, for example? Or...
Yeah, that's a good question. So I don't think, so I think the first thing is we first found if there are any, whether we can find a signal. The second thing is what kind of models predict that kind of signal. So if we have other models also predict this kind of bubble-like behavior on a semi-sky map, you also get a similar signals. And I don't know any yet, but there could be any other models generate this bubble behavior like here. And I'm very interested to hear that. And also we can use similar search strategies to look for those models. So in this case, we want to build up a search strategies generically looking for these features on CMB scanner. Actually, that's why I want to comment on this future work.
But the bubble behavior we can pick up on.
Yeah, so that's why the future work, I'm hoping to work on that. So I don't know the conclusion yet. So that's why here I give some hints for the path toward that. So the future directions we're looking for is how to find out these kind of features on CMB scanner. If you look at it by eye, it looks very obvious there's some features there. But actually, now we are all of the statistics are really going to the Fourier space. We're going to a 2-point function, 3-point function, or even higher point functions. But actually, that kind of analysis is good for some cases, but it's not good to pick up these kind of signals. Because we did calculate our endpoint functions, actually they will be show up in endpoint functions. So you might say you should always do analysis to endpoint function, but that's not sufficient efficient. Maybe there's another way we consider is we should probably go to the position space. We directly search for the signals in the position space of semi-sky map. And that might be a better way to look for this kind of features in the position space. And because I'm at Rutgers, and Rutgers now center become a machine learning center. So people are interested in machine learning techniques, and machine learning techniques have been proven to be good to find some features or anomalies in the images. So here I say imaging. So I put in this image into maybe ask some machine learning techniques. Maybe the machine can tell us directly what is the features in this kind of or anomalies in this kind of map without going to this 1.2 or 2.3 point endpoint functions. So maybe that is more efficient way to find out this kind of features in the same sky map. So in essence, it's more like a generic search. It's not specific to this model, but any features that has some particular structures in this position space. Okay, that is one direction I'm excited about. Another direction is how to link that to gravitational waves we studied before. So actually, if we consider this type of phase transitions, we can get additional features in the gravitational power spectrum. Here I showed you the picture of the energy density of the gravitational waves as a function of the k vector. Here I showed this. This is a cartoon picture of the usual gravitational wave spectrum from bubble collisions, and that will hint to the scale when the phase is complete. So this is usually use some envelope approximations. Anything that's for the bubble collisions, you will get this kind of behavior, and that's one of the targets for LISA or the PDA or anything. We argue that if the phase transition generate these things actually start during inflation, under this kind of non-thermal phase transition we consider, you could also have this kind of longer tail of the gravitational waves from the second order perturbations once those modes re-enter quality. So in addition to the usual bubble collisions, from phase transitions. There's another part from the perturbation of the biggest bubbles. And once they range to the horizon through the second order perturbations, they can also source gravitational waves. And that power spectrum is something like this. It's more like flattish and extend to much larger scales. So if we can, so that means this one, either we can directly measure it or you'll be constrained by CMB. So if we see in the future of this bubble condition behavior and hint to some kind of scale of phase transitions, we should check from the CMB measurements and whether this is consistent with that kind of scales. And if we correlate these two scales, we can also probe or give a hint what is the scale of the inflation, because what's the size of this is correspond to the size of a scale of the inflation. Okay, so we have interesting correlation of these two type of gravitational wave signals from first order phase transitions. Okay, so I think naturally close to the end of my talk. Probably also the time. I can summarize. So in this talk, I introduce a slow first order phase transition during inflation, and that can generate dark radiation isocurvature, which are visible in CMB. And once we consider this kind of dark radiation isocurvature, you could put a much stronger bound on the delta effective than the usual adiabatic ones. And this dark radiation isocurvature generate interesting features in the position space in the CMB sky map. And we need dedicated searches to look for these kind of features, or particularly in the non-Gaussianities in the CMB sky map. And here I showed you these two cartoon pictures of our talk, and then I'll stop here. I'm happy to take more questions.
I wasn't quite clear on exactly how tuned the rate of the production of these bubbles needs to be during inflation. My gut instinct tells me that there's some tuning going on in here, but maybe there's not, and I'm just trying to see if there is one and what it is.
T star over T.
Well, T star over T is, yeah, that's.
I think let's
one.
go
Is
back
that the
to.
only one?
So it's more like yes, actually it goes back to this changes. So what is controls the amplitude is this ratio. And so I think there is another, I think to answer that, there's one thing is, did you consider this because now we put a constraint. Is anything below that is safe? Anything above that is ruled out. So if we only consider a constraint, so it's like one-sided, so anything below that, we can easily get a very small rate by cranking this mu to small. Because this is exponential, to be easy to get that small. Whereas if you look, you are saying it's currently safe now, but if you want to see a signal in the future, so there's a window that you are leaving, because you are not ruled out now, and you will be visible in the future. There is a window. In order, if you want to put in that window, you need sort of select this gamma over Hubble force to be a particular value. That means you choose a particular value of mu. Then you might say, okay, there might be some exponential here. So that's why you might say there's some retuning. So in that sense, yes, but I think to answer that is so that there are additional parameters in those models. So you can always play with additional parameters and then to absorb that kind of sensitivities to others to make it to be make this computation to be in the window that is visible in the future. But I agree that will be more tuned than if you just consider constraint.
So related, I mean, that was about the amplitude, but what about the Ki? So how is that tuned for it to be somewhere near the pivot scale?
Good. So I think this is, let me go back.
You mentioned it, but
Yeah. So we only need to be the Ri or this Ki to be around the CMB or larger. So you also like one-sided of like a choice. So if the Ki Ri is much smaller than the CMB, of course no signals.
right,
If it's
but
larger-
that comes back to, I think, what Marius was asking, right? So if it's
if it's
too
too large,
large, then would it not be homogeneous? I mean,
Yeah.
how should I think about that? Is that a tuning?
But I think there's a big window in there. So here, so I think about the CMB size. Yeah. So okay. So that is so KPV is 0.05 inverse microsecond, whereas the moving horizon now is more like 10 to the minus 4. So there is a window of that. Once now is your KI is within that window, this constraint will apply. So it's 10 to the minus 2 to 10 to the minus 4 in essence.
Right, but the energy scale is doing it. The Hubble scale during inflation by construction is not changing very much, right? So is it not a coincidence that the phase transition, you know, you say yes, it's 2 orders of magnitude in co-moving K, but in energy density, it's very little, right? Because it's slow roll inflation. So is it a coincidence that the phase transition starts during that
Okay,
narrow
so
slice of energy?
I think energy density might be small different, but what really cares here is the phi I. I think it will runs. I think it also runs to a significant order 1 fractions of phi field.
Right,
That's
so in this
phi-
model, it's
Yes,
it's
phi I is not Hubble. Yeah, it's not for the Hubble. It's for phi I.
But if you want this to be generic, it better be triggered by the field excursion and not the changes in Hubble, right?
Yes. Yeah. This is a field excursion. So this is phi. And so when the field passes through some field value, it switches on, and so it's not like a Hubble minus Hubble.
No, I understand,
Yeah.
but let's say if you wanted to generalize this model, it better be like something similar to this and not,
Oh yeah.
you need some non-minimal coupling of the input on.
Yes, yeah. You always need to couple to influence on this. Yes.
Can you go back to the power spectrum plot? Because I have a comment, but it may be irrelevant based on the answer to my question.
I mean this one. Or...
Yeah, so how big is the boost over the usual adiabatic power spectrum at high K?
Depending on so this is plateau, depending on your gamma PT. Right. So this is the parameter that we sort of in the model, and also in order to scan, we make it a free parameter. So what we let the data tell us what is the constraint on this parameter. So of course, gamma PT is large, you get a large boost. If gamma PT is small, you get a small contribution to that. And maybe just give you a hint about what is the constraint. The constraint is like delta effective times FISO order 1, which order 1 meaning is FISO is relative to adiabatic ones. So the amplitude of isocurvature should be not so much stronger than the adiabatic ones. So adiabatic is 10 to the minus 9, and this one is like sort of roughly the same order of that, if you consider not too small delta effect.
But for small gamma PT, it's a big boost. Am I? No,
No, small. Yeah. So this is the parameter, and I'm talking about what is constraint.
Yeah.
The constraint is like the isocurvature power spectrum cannot be so large compared to adiabatic ones. Right. Yeah, so in this case, it's a model. You can put it, if your model predicts a much larger gamma PT, it will be ruled out. Yeah.
For the future directions, have you thought about second order phase transitions? Like you can create these like defects also during say inflation. These can also get stretched out. And many of these can nucleate one defect on top of the other. And gamma PT is also constant for those you can show. It's a ratio of like the scales of the mass of the monopole string or wall to string.
So how would this, what's the phase value or decay?
The gravitational waves.
Decay gravitational.
So that's
yes,
radiation.
Yeah, that's dark radiation. Yes.
Yeah.
Indeed. Yeah, indeed, I would say that also generates sort of dark isocurvature from that. But we need to calculate what is the power spectrum of that. So I don't know whether you have that in top of your mind, but that's interesting to look for. Yeah, to study that. Yeah. Very good question. Very good comment.
Any last questions? Okay. Not, let's thank Peizhi again.
We got it all.